All right. Oh, oh, hmm. Yep, there we are. So we're recording now. So today we're just going to continue with the lecture and continue with the first lab. I will create the assignment today, and we'll go over all those details. Um, so yeah. So this is, if you remember the GitHub, right, repository, this is really important as it contains all the code. These are all the notes, right? So you also have them a lot of these on Brightspace, but this is essentially the notes that I will cover. Okay, so like I like to write like on the whiteboard kind of a situation, but this is the transcribed set of notes. So today we're going to cover essentially, so we were somewhere around here, XOR, perfect secrecy. We've done examples of XOR. So we'll probably, I think we start here. We'll do this as kind of just a little practical thing to think about some things, and we're going to talk about what is perfect secrecy, Claude Shannon's contributions. Okay, so all this is defined. Shannon's limitations. We're going to talk about the one-time pad, by Claude Shannon. Um, pros and cons of it. And then this week's on Thursday, we're going to do our first Python lab where we're going to cover our first encryption, just a warm up. This is actually not modern cryptography, but it's going to be, kind of old cryptography, but it's actually a pretty important example. So it's meant to get everyone on the same page. Many of our block cipher algorithms are going to be similar to this approach. But here we start with something very simple, very, very simple, that actually can be hard to implement in code so that you can, and it's totally insecure, by the way, very insecure. So, but this is where we'll start, and the code is here and so on, and the notes. Okay. Yeah, and then hash functions and message integrity. I don't think I'll start this today. This is probably next week. All right, we'll pick up here. But as I said, so this is just you can check out the GitHub where the lecture notes are provided, or also Brightspace. All right. Yeah, so on the agenda today, I will do a little bit of lecture, and then we'll switch over to the lab, right? So I want to finish that first lab, the last two problems, I think, which were the padding and corrupting one bit. And so we're going to do that. And then, just going slowly through the first lab just to make sure everyone is on the same page. Essentially, you can ask enough questions. Right. Any questions before I get started? Nope. All right. Good. So now I'm going to switch over to the whiteboard. The last thing we cover, I believe, was going back to here. I think the last thing we covered, yeah, so I know we did XOR samples, yeah, and this, right? So I went over symmetric encryption, kind of gave you a formalized version of it in the previous lecture, what everything is. Okay. So that's been defined. And we went over the XOR operations. So yeah, so then I'll start with just an exercise as an example, kind of get our brains thinking about this, interesting ideas. Okay. And then the one-time pad, that's really our main goal to understand. All right, so I will, like I said, you have these notes electronically, but I will switch to the whiteboard just because it helps me to think better. All right, so I'm going to go to new whiteboard. Awesome. Okay, so we were doing XOR, and I'll just do kind of a refresher on XOR operation. This is something that eventually in a couple of weeks we will have to learn how to do in code. Okay, so let's do this in code. So let's think through this exercise. So we'll have, again, a message, right? Message, which is the plain text message, and we have a key. Okay. So then I'm going to have 0, 1, 1, 0, 1, 1, 1. Then I have the key 1, 0, 1, 1. And then I have 0, 0, 1. Okay. So we XOR it. Okay, and that gives us a cipher. Gives us a cipher, which is going to be 1, 1, 0, 1. And then this is 1, 1, and that's a 0, right? So that's the cipher. So this is the thing that you need to send. So that was the encryption. Now we do the decryption part, which we can denote as key with cipher, right? Some kind of an algorithm. So in this case, just the XOR operation. So we're going to denote it as K XOR C. All right, so let's do the decryption. So I'm going to start with the cipher. Okay, so I have my cipher, which is this one over here. So that's going to be 1101 110. Okay, I need the key, right? And that's going to be that same key. So 1011 001. And I can obtain the message or plain text. The message. All right, and that's going to be 0110. Okay, and then all these 1, which is the same thing, right? So it should be, oops, same thing, right? So yeah, they match perfectly. Okay, so that's just a warm up, just an idea. Now let's do like a thought experiment, right? Let's think through an idea here, and let's see what you guys think about it. All right, so I'm going to go back to the notes here. All right, share the screen just to kind of give you the idea. So that's going to be, we just did this, right? So now we're going to think of this sort of a quiz example, right? And I will lay out the idea, but we're not doing a quiz. We're just a problem, essentially. All right, so I'm going to go over here. And so let's think about this. So let's imagine, so a lot of the cryptography is about like breaking things, right? So, you're trying to protect your information, but a lot of the time we're thinking, okay, how can I break this idea? So let's say that you want the key for something, right? So you want the key, the secret key. So let's kind of think of this as a problem or exercise. Okay, so let's say you are given a message. So you are given a message M, right? You're given a message M, and you're also given its cipher and the cipher C. So the question then is, can you compute the key from M and C? So the question is, can you compute the key EK from M and C? What do you guys think? What would be your answer? How do you even begin to answer this? You see what I'm saying? All right, so somehow you were able to get the cipher and the message. Could you get the key? Why is this relevant? Well, there might be other ciphers going out there, right? So you just capture like one block. So what do we know? So let's just kind of lay this out, right? So what we know so far, there was a huge message, but we know that that message is broken up into blocks, right? Dot, dot, dot. And then there was some kind of a key that was used, and the key matches the size of the block. So what might be the advantage of something like this? Well, if we had a message block and we had, you know, we don't have the key, but we have maybe the cipher of it corresponding to that block. Well, maybe if we were able to get the key, then what about when we capture this other cipher block? Could we use that key to maybe get that message? And so we break the whole thing. Go ahead, please.
If you export both of them, you get the key. Like if you export the cipher and the like message,
Mm-hmm.
wouldn't you get the like key value?
Yeah. Yeah, exactly. Good answer. Right. Exactly. So let's think it through. All right. So that's why I did the exercise before, right? So before I had this, so his theory, right? So I'm saying what? I captured the message. What was that? 0, 1, 1, 0, 1, 1, 1, correct? And then I also captured the cipher, right? That's what the problem is saying. 1, 1, 0, 1, 1, 1, 0. So what you're proposing is I'm going to XOR both of these, and maybe I can get the key, right? And so, well, let's try it out. So the message is 0, 1, 1, 0, 1, 1, 1. The cipher is 1, 1, 0, 1, 1, 0. So the key here then should be 1, 0, 1, 1, 0, 0, 1. And if we compare it to the key, it matches, right? Do you guys see that? So, so wow, that's like amazing, right? So all you need to do is grab a cipher that's going around and then maybe just get one plain text that corresponds to it, and boom, problem solved. So obviously that means, our approach is insecure because, we don't want that. So yes, in this case, we can get the key, right? And this type of encryption is ECB, which is electronic code book, which if you remember is the same type of encryption that gave us the image, that we were able to still see the image. Do you see that? So it's pretty insecure. So even though we can do it, right, we can break it, we don't want to be able to break it. So that means instead of using an algorithm such as ECB, we need to switch over to another one like CBC. All right, so we will see later on how that works, but for now, I'll just give you a basic intuition of it. So we have ECB, and it's pretty simple. And then we have, let's say down here, CBC. Okay, so what happens is, we have a block. So this is the message, right? And we have some kind of a key. So we have blocks here. So this is block 1, block 2, block 3, right? And we XOR with the key. Oops. And that produces cipher 1, cipher 2, cipher 3. So we just saw with the previous exercise that there's a vulnerability in that approach. So we definitely don't want to use that. So instead, in CBC, we have kind of this similar idea. We have message, key. I'm going to have block 1, block 2, block 3. And I'm going to XOR with the key, same key. right? So this is the key to produce C1, but there's going to be an additional step. So I'll do it here. So this is going to be C2. C2 actually is also XOR. Do you see that? So this is um, the improvement from ECB to CBC. And CBC is just like this. So like if we just broke one, then we have the key for all the other ones and we can break them. But now this one, the C3 that comes here is the result of XORing B3 with the key, but also with the previous C2. And so that means for this one, we would get a C1, right, here. And then this C1 gets XORed with the next one. Do you see that? So now the problem is, what about the first one? What does the first one, because in this algorithm, the first one also needs some kind of a vector, right, for us to be consistent. So we need another vector that comes in here for B1. So B1 gets XORed with the key, but also gets XORed with some other vector to produce C1. Then this C1 is used in the next iteration, B2 key and C1. So the name of this one is div. So if you remember, we had something called the initialization vector in the lab that we did last week, and that's what the initialization vector is for. Make sense? So that's essentially the idea. div. All right, so now you have a sense, you've seen ECB as visually, right? You saw images and you saw it's insecure. You also saw that you can essentially very easily, if you just have one, for some reason, let's just say it's like like a Tom Cruise Mission Impossible kind of a thing, right? So they break in, grab one cipher and one plain text, they XOR those two, they get the key, they would be able to break everything. So that's obviously a very insecure cipher, but you just strengthen the cryptography by adding a better algorithm. Any questions on this idea? Pretty easy. All right, so we'll come back to this as we start looking at symmetric algorithms, but essentially you've seen we've added some complexity to the algorithm. Initially, we just had XOR. Now we have a more complex algorithm that looks at the previous key. At some point later in the semester, you guys will implement this approach. Okay, so you'll see how it works. All right, so that's the example. Pretty straightforward. So we're going to see that there's actually, whenever you're, we know, for instance, that messages are going to be very long, right? So like I gave you the example of a movie. A movie is very long, still needs to be encrypted, right? Because it's, copyrighted material. And so the idea so far is that we break it into blocks and we XOR it with a key. But this gentleman named Claude Shannon, he decided to think even more broadly, right? So we're going to start with his initial ideas of modern cryptography. All right, so let's go ahead and do that. So there is basically classic cryptography, and then there's modern cryptography, and then there's going to be quantum, I guess. All right, so quantum cryptography is, I would say cryptography that still doesn't exist, but people are concerned that maybe in the classified world, they already built a quantum computer, and in the public world, they're very close to creating a quantum computer, right? So if, as we will see later in the semester, if somebody breaks or creates an actual quantum computer, theoretically already, there's algorithms that can break cryptography. There's an algorithm called Shor's algorithm that I think I mentioned before, Shor's algorithm, right? And this one already knows how to break RSA. Okay, And so that's, that's why I'm saying there's three classifications. One, two, three. Quantum cryptography requires a quantum computer, which I don't think it exists yet, unless it's in the classified world, right? And they're keeping it secret. Um, there's companies definitely that say Google, uh, that say that they're very close to building a quantum computer, so it is concerning. So there's an effort right now to build what are called quantum ready algorithms, right? Because otherwise, as you will see later on, that will cause a lot of disruption. But this is more at a stage of research, I would say. There might be like 10 algorithms out there that say that they're quantum ready, but there's a lot of research going on. So maybe today, somebody says we have a quantum ready algorithm, and 6 months from now, somebody shows that it has a vulnerability and they break it, right? So it's kind of this little game of I propose an idea, I think it works, and then somebody says, no, it doesn't work. So they're working on it, okay? There's also, so that's quantum. Then there's also classical, which we will see an example of classical cryptography on Thursday. We're going to do the substitution cipher. So I'll go over that algorithm. We'll implement it in Python. You guys will see that even though that algorithm is pretty insecure, it's still hard to implement, right? So hardness, the point there is just because something is hard to implement doesn't mean that it's secure. Do you see what I'm saying? So complexity, obscurity, hard to code does not equal secure. Okay. And so, but we'll talk about, that one just to kind of this, the only classical algorithm that we will discuss in this course, because I think it's good as a practice of Python before we move on. And then we have the modern algorithms, right? Which are the ones that, so the research or the proposals for these started around 1917, but it was more like at a research state. Still during the Second World War, if you've ever heard of the Enigma machine, which we get a person from the NSA that comes every year to campus and they bring an Enigma machine. So if you're curious, I think they actually do it in this semester in the fall. So you can go talk to them and see an actual Enigma machine from the Second World War. But even this machine was still classical. Okay, this was broken by the first computer made by Turing, right? But as you can see, with cryptography is always this idea. Let's break it. Let's break it somehow. You know. But anyway, so people would just create these elaborate schemes or mechanisms to encrypt data, to jumble the data, etc. But computers proved that, before, without computers, it was more of a manual process. So it was harder. With computers, obviously, computers are good at finding patterns. So classical algorithms kind of went away with computers, right? Kind of this idea. But then you had already the research that Claude Shannon started. And so that's what we're going to start with right now. Okay. So we're going to focus on modern cryptography mostly in this course, right? So that's going to be the main focus. All right. So as we established, the core of cryptography is, for the full communication, we need a secret key and then establishing a secret key, right? We talked about that. How do we share the secret key? And then once the secret key has been shared, then you use secure communication with the established secret key. All right, so we're going to just give some definitions here I'm going to start with symmetric ciphers. So we're going to ignore the secret key establishment step for now and just focus on secure communication with the established key. All right, so this is going to be under symmetric ciphers. Okay, so symmetric ciphers. So what is a cipher? A cipher is defined as a pair of efficient algorithms ED, right? So a cipher is a set of efficient algorithms E comma D, where these are going to be the encryption and decryption algorithm. Okay. So where we have E encryption, K comma M gives us the cipher C, and the decryption is K C, right? To produce the plain text message. And this has to be subject to something called the consistency equation. So given, which has to be exact, so equal. So given the consistency equation, which is D is K, comma, E, K, comma, M, which is equal to M, right? So this has to hold exactly, right? So obviously EKM gives you the cipher, and then K cipher decrypted gives you the plain text message M. All right, so this is the consistency equation. So just a couple of things here. So E is often so it uses some kind of a key for the encryption, and then D will use the same key for the decryption. So let's take a look now. So now going back to this idea. So let's discuss an example of a secure cipher. So what is a secure cipher? Right? So what is a secure cipher? So actually, that's kind of the idea. Okay. So Claude Shannon in 1917, Claude Shannon, around that time, he started thinking about this problem, right? So what exactly is security? What is a secure cipher? And he started with one simple idea, which has a name. It's called the OTP, which stands for the one-time pad. One-time pad. All right. And essentially, the key idea is that you're going to use the same approach we've been discussing. So KM, and just keep it simple. Don't even go into complex algorithms or anything like that. Just look at the XOR operation. Okay. So essentially, what Claude Shannon studied was that you have a message, not a block, right? So the actual message, and he wanted to create a message as long as it needed to be. Maybe it was a book, maybe it was a movie, whatever it was. But he was going to start with creating a key as long as the movie or as long as the book. Do you see that? So instead of just breaking the message into blocks, trees, what if I just take the whole message and create a key as long as the message? All right, so that's essentially one of the definitions in the one-time pad. So you have a key, which is, and this is really important, by the way, it has to be a random sequence of bits, as long as the message. As long as the message. So that's, how he started to study this. And so he applies the XOR operation. Okay, that's the one-time pad. So he starts to think about this, right? So is the one-time pad secure, right? And so that takes him to the really profound question of what is a good cipher. And so he concluded actually that it was secure, right? So that his research concluded that a message, a key, as long as the message, and that is 100% random, right? Random, was in fact secure. Okay? So it's that simple, right? So it is secure. Okay. But what's the problem? Yeah, go ahead. Impossible to crack, yes. He concluded exactly that with the one-time pad. But key things though. So in the one-time pad OTP, two things are pretty important. The key is 100% random, right? Random. Another thing is you only use it once. So you only use it once. You cannot reuse it. And then number three, the length of it has to be, so the length of the key has to be greater than or equal to the length of the message. Yeah. So, okay, let's say for computers can't really produce totally random keys, first of all, right? We all know that. But let's not even go there. Let's ignore that part. Let's say you have a quantum computer that can create a perfect random sequence. Okay. So that's kind of questionable. You only use it once. Okay, you could potentially only use it once. But this is the problem. You can't really make a key that is as long as the message, right? So it's impractical. And so that's what, so even though Claude Shannon concluded that, you know, in the OTP was secure, as long as the key is 100% random, you only use it once, and the length of the key is greater than the length of the message, you have security. It's just not practical. And so that's why, you know, if this was practical, then this would be encryption. Do you see that? Like, why create other algorithms? Let's just do it like this. But at the end of the day, you will always see that cryptography is influenced heavily by performance, right? Or convenient things. So, you know, imagine if you're downloading, just to give you an example, again, that movie, F1, right? It's a 3 hour long movie on Netflix. Well, first you'd have to download the key, which is just as long, right? And then you would have to, so it wouldn't be practical. You'd be essentially downloading the movie twice if you think about it in terms of the sequence of bits. Do you guys see that? So that would, and now imagine the whole internet, all of you watching a movie, the same movie at the same time. So you're doubling up the internet consumption. Do you guys see that? So the whole internet would be requiring like double the amount of data that gets downloaded. Do you guys see that? So obviously not practical. And that's just an exaggerated case, but that's the idea. So essentially then, what's the solution? This is, you know, he concluded that it achieves perfect secrecy, but it's impractical. So therefore, what we do is we take the message, break it into blocks, and XOR, you know, smaller keys with those blocks. But that essentially means that that approach is less secure than Claude Shannon's approach. Therefore, we do things, right? Like that's why we have to add additional complexity, right? Like the example here, this example, right? So here, if the key was as long as the message, this would work just fine. But unfortunately, it can't be as long as the message. So we have to break it up into blocks, and that means it's less secure. So then we have to take an approach like this, which adds complexity to the algorithm by using the previously produced cipher. Questions? Does that make sense? Yeah, go ahead, please.
So is this a form of cipher used for shorter messages where the key is it's potentially able to make a key as big as the message?
Yeah, if you could, yeah, I guess, yeah, you could do that. But so what would be a use case for that approach? Let's say that you say, I want to use only the one-time pad, but only for small things. What would you use it for?
Well, like our lab. Would that work for just like our lab? Because it's only like 46 bits.
Well, yeah, but okay. Um, so what's your question though? Like, does that achieve perfect security?
Yeah.
Yeah, I would say that if you only use it once, if it's truly random and it's the same length as the message, it achieves security there, but you still have the problem of sharing the key. And if going back to the idea of sharing the movie, right? The movie and having a key as long as the movie. So the other problem is you would have to share that key securely. So you actually have to encrypt that thing. And what would you use for it? And we don't actually have an algorithm for something like that because RSA, which is the thing that we use to exchange the key, only works with small things. You see that? So there's all these problems, right? And it's kind of like, yeah, there's achievable total security, but it's not practical. Any other questions, guys? So this is the starting point, right? So this is where you can, in your mind, if you want to say, well, okay, what is perfect secrecy? Claude Shannon said and concluded the OTP, the one-time password, achieves perfect secrecy, but as long as it meets these conditions. Key is 100% random. This is a serious problem in cryptography because computers only do pseudo-random. So actually, it's a serious problem to be tackled. You only use it once. That's another problem that you have to deal with. And then the length of the key would have to be greater than or equal to the length of the message. All right? All right, so that's our starting point. We obviously can't do this, so our algorithms are a little less secure. Therefore, we have to add some kind of complexity, and that's where the whole complication of the algorithms comes in. All right, so let me go over my notes. All right, so I'll kind of summarize. So it's the one-time secure, the one-time pad, sorry, or OTP. So that takes us to the more profound question of what is a good cipher. So what makes a cipher secure? So Claude Shannon, who's the father of information theory around between 1917 and 49, you can see it's right after the Second World War, was studying these ideas. So one of the key things, though, that he posted is that the ciphertext should reveal no information about the plain text. And we've already talked about this, right? We looked at the example of the image. You guys could see the square and the circle, and that was revealing information about the cipher. So it broke one of his main assumptions, okay? So the basic idea, the ciphertext should reveal no information about the plain text. All right? So essentially, Claude Shannon did come up with a formulation of what is a secure cipher, right? So there's a way. So, a lot of the time when you can't create, like physical equations about things, you use probabilities, right? So essentially he came up with a relationship based on probabilities about what that you can use to measure if something is secure. Okay. So we're going to take a look at that. So he came up with the following definition. So Shannon, for security, Shannon, right? Claude Shannon, came up with the following definition. Okay. A cipher, E comma D, remember it's a pair of algorithms over, this just means the key set, the message set, and the cipher set. So just all possible keys, all possible messages, all possible ciphers, has perfect secrecy. That's like saying a lot, right? It has perfect secrecy if the following happens. So I'll let you guys think about this formulation for a little bit. So I'll write it down, and then you guys can tell me what you think it means, right? So let's take a look. But this is what he wrote. So that's it. This is his like definition of security. For any cipher where you have an algorithm E and D, and you're going to have keys, messages, and ciphers. So a cipher has perfect secrecy if it meets this condition. So what do you think this means? How would how would you interpret this? And PR means, as I said, probability. PR is probability. Oh, please go ahead.
If the probability of like any key to any message equals, I don't, I had a way to word it, and I know.
Yeah, no, I get it. It's tricky. It's tricky. It's simple, but it's tricky to visualize initially. So there's some kind, so break it down into the parts. So you're comparing two probabilities, right? And you have the same encryption algorithm, you have the same key, you have the same cipher. It's similar to the example we were looking at before, but you have, remember, M is the plain text. So you have two plain text messages, M0, but also M1, right? So they're not equal, right? Anyone else want to give it a shot? So what this is saying essentially is that the cipher should not reveal anything about the plain text message. Do you see that? So the probability that it came from M0 should be the same as the probability that it came from M1 if the cipher is really secure. Do you guys see that? So that's essentially what he is saying here. So given the cipher text, you cannot tell if message is M0 or M1, right? So it would be pretty bad if this was like, well, I from this cipher, let's say that you have the cipher and you look at it and you cryptanalytics and you say, you know what? I see something in this cipher that tells me that it's more one over the other. Do you see that? That would be really bad. Because then you start to do that a lot and eventually you can break it, right? So it has to be equal. It has to be an equal probability that, and that essentially just means that you can't tell anything from it. So that goes back to the example of that we did on last week where we had the image of the squares and the circles. Obviously, you could tell, right, that this message or this cipher, sorry, looks like this message M0 or over another one. All right, so that's the definition. So the probability is the same. So if you are an attacker and you intercept a particular cipher text, then in reality, the probability that the decryption of C is M0 is exactly the same as the probability that the decryption will give you M1, right? You have no, so if all you have is the cipher text, then you have no idea whether the cipher text came from M0 or M1. That's essentially what that means. Okay? So that's a way that you can quantify, the security of an algorithm. All right? Yeah, and like I said, in his conclusions, Claude Shannon said the OTP has perfect secrecy, but he also proved that you have perfect secrecy. To have perfect secrecy, the length of the key needed to be greater than or equal to the length of the message, and this is not efficient. But as you can see from this idea, pretty much everyone started developing all the algorithms that we have today. So a lot of the algorithms are going to be based on this idea of XORing. They're going to be keys that are, the keys you want them to get as big as possible given your constraints. And so this will, we can expand to more complexity in the algorithm, right? To try to achieve more security and various other things that we can do. All right, so that's the definition of what is a secure cipher. Any questions? All right, and this is the metric that he proposed, essentially. Let me erase this. Okay. All right, so that's kind of the introduction to the topic. All right. All right, the next thing we're going to do today, so we kind of did a little bit of a lecture there, and now we're just going to switch over to the lab and finish up the last two problems that we were working on, which was corrupting one bit, I think, and then also padding, okay? And then after that, yeah, we should be done with that assignment. All right, so I'm going to stop this.